Hi everyone, my name is Jason and I'm pleased to present our paper, A Priority Map for Vision and Language Navigation with Trajectory Plans and Feature Location Cues. This is research that was co-supervised by Leonardo Impet from the University of Cambridge and supervised overall by Rico Zenrich at the University of Zurich. Our paper addresses transformer-based approaches in vision and language navigation. And we do this by focusing on the touchdown benchmark shown on the left-hand side. So in this task, an agent is given a language instruction to navigate an environment generated from Google Street View images. But in this case, the instruction is given as a single block of text. And this means there's no alignment between this input and each visual point as the agent moves through the environment. This challenge is an example of a problem in many cross-modal tasks, and in fact of any task where events unfold over time. In these cases, agents are required to align and learn across discrete points in corresponding sequences of inputs. Transformers are a natural choice for sequence modeling, but in the case of vision and language problems, standard models are designed to deal with the spatial dimension, for example, which part of a single image to focus on, and in doing so, leave aside the critical temporal dimension of this class of tasks. We address this problem directly by taking inspiration from a mechanism described in neurobiological studies called a priority map. And this cortical loop mediates over high-level goals and lower-level cues on salient features. And it helps humans and other primates to identify relevant information as they move through the world. Our implementation of a priority map takes the form of two submodules. The first takes a new type of input called a path trace, and this is a high-level view of the route that is being navigated. And with this, the submodule generates a top-down plan of the trajectory. In the second step, a series of operations are applied to the visual and linguistic inputs. This begins with a learned boosting process that enhances salient features in view. And the output of this step is then used to pinpoint a span in the remaining text. The outcome is that the features in each modality are both synchronized to each other and to the current points in the trajectory. Our priority map module is a component in a novel framework that takes the input of a transformer-based model and combines this with the output of the prioritization process. An advantage of our approach is that individual components of the priority map can be trained on very small sets of in-domain samples. This is in contrast to the prevailing paradigm for transformer-based architectures, where we've seen the size of datasets for pre-training scaling up over time. The outcome is that our system can be trained in a matter of hours and with limited computational resources. On the test set, we can see that our best performing variant, which is visible at the top of the chart here, manages to complete over a third of the routes in touchdown, and this is a doubling on the result attained by the previous leading system based on transformers, which is shown at the bottom of the figure in green. A comparison of the purple and grey bars also demonstrates how our framework adds major gains to the performance of cross-modal transformers, both for general vision and language models, so for example the visual BERT architecture, and also for purpose-built architectures such as the VLN transformer from Zhu and colleagues. Both code and the datasets are openly available for further investigation at the links shown below. Please feel free to contact me if you would like to talk about this research in more detail. We would like to thank you for your time and interest.